So we're going to continue our discussion of acids and bases, and now we're going to talk about the acidic and basic behavior of salts. And you'll see what I mean in a second, or in a little bit, when we talk about a salt and how we could sort of see that there are acids and bases inside salts. But before we get there, we kind of have to establish some ideas. Um, and so it starts again with understanding that weak species behavior and strong species behavior, they differ. And so because the species behavior differs, the conjugate behavior differs as well. It turns out, and again, until you see it, it's kind of hard to see. It turns out that salts are made of conjugates. Okay? So if we understand how the conjugates behave for weak species, and we understand how the conjugates behave for strong species, then we'll understand the acidic and basic behavior inside a salt. So just to remind you, all right, conjugates of weak species, they are acids and bases themselves. If I look here, here's our general expression for the acidic behavior of a general weak acid HA. And here is the basic behavior for a general weak base B. We wrote these down before. We know how to come up with these just, whenever we need them, okay? Notice that because they're weak, we have a double arrow. Now, what this double arrow entails and what it implies is that the reaction could go this way or it could come back the other way. So the fact that this part exists in each one of these reactions, the fact that there's a way backwards to the reactant side, that tells you for this acidic, right, reaction, this conjugate base, it really is a base. It can act to pick up an H from H3O plus and go in that direction, right? This isn't really new, but it's something that we definitely have to stress. This for sure has basic properties. It can pick up an H, all right? Same thing with this base reaction. It could go this way or it could come back this way. There's a double arrow there. So for the base reaction, we see that we make this conjugate acid. This guy right here is definitely an acid. It has the ability to give away its H plus to the OH minus and go in that direction. The conjugates of weak species are acids and bases. Now you can kind of see maybe how they show up in salts. What's a salt? It's a plus and a minus stuck together. These things, when they show up in solution, they themselves are acids and bases. They're weak acids and bases. These conjugates of weak species are themselves weak species. And so we need to be able to talk about their chemistry and do ice table calculations with them. But before we get there, in terms of how we approach that problem, we need to know that for strong species, the behavior is different. The conjugates of strong species are not acids and bases. And you remember when we're dealing with strong species, we even write the chemistry different. We treat it like a dissociation, like a limiting reactant problem that's just going completely to the right. Notice, not Cl minus. Notice for this guy down here, just a general HA. I had HCl in my head when I was writing that. For a general strong acid, HA, where A is just a general anion, one from our list, it dissociates completely to the right-hand side. We're going to get H plus and an A minus out. There's only a single arrow here. Is it possible for this A minus to pick up the H plus and go in the other direction? No. So this conjugate that we've made, all right, the conjugate species here, because it came from a strong species, this is not an acid or a base, all right? It's not going to affect the acidity or basicity on this level of chemistry at all. Same thing with this M plus that gets generated from our strong base reaction. This M plus, can it somehow pick up the OH minus and go back the other way? Well, no. We would consider this, even though it doesn't fit our definition, we would consider it a conjugate of a strong species. It's involved in this reaction, but the big thing here is, all right, these soluble hydroxides that make up our strong bases, those metals themselves are not acids and bases. Conjugates of strong species, all right, the things that end up on the right-hand side, all right, from strong reactions, from full dissociations, They are not acids and bases. Okay? So this is a general idea. Again, we have to have in our head weak species and strong species, they behave differently. And because of that, their conjugates behave differently. So then what is our mathematical approach for calculating like the pH of a salt solution? Well, what we have to realize is that Ka and Kb for a conjugate acid-base pair, so a conjugate acid and, an acid and its conjugate base, or a base and its conjugate acid, Ka and Kb for that situation, they relate through Kw. And I'm just going to show you a quick little derivation that kind of proves that. If I write my general acid reaction again, okay, for my weak acid HA, remember it has to be a weak acid, there's going to be a Ka associated with this. It has to be a weak acid to have an equilibrium, to have a double arrow. There's a Ka associated with this reaction. I just got done saying that this conjugate that you make over here, this A minus, because it's involved in a weak reaction, it's definitely a base. Underneath this, let's write how A minus acts like a base. Well, what do we do with bases? We always react them with water. One of the products is always OH minus, and the other product is the conjugate acid. Well, what's the conjugate acid of A minus? Remember, to make a conjugate acid, you gather up an H plus from somewhere else. It's HA. This reaction right here is how A minus, this conjugate species, acts like a base. If it's acting like a base and it's making OH minus, it has a Kb associated with it. All right? Now look what happens when we take these two reactions and we add them together. All right? And remember our rules for manipulations of K when we do this. If we add these guys together, notice A minus cancels from here. HA cancels from here. We get 2H2O on this side is in equilibrium with H3O plus and OH minus. And remember from our chapter, when we add reactions, what do we do with the individual Ks? The K here that we would get in the end, our new K, would equal Ka times Kb. So remember, when we add reactions together, we end up multiplying the individual Ks. But this reaction right here, we recognize this looks like how water dissolves in itself. It looks like the autoionization of water. And we know that this K is Kw. So from this math, when I add these together, the K I get should be Ka times Kb, but then I generate a reaction that I recognize that has a KKW, and so that means that Kw is Ka times Kb. Right? And this is a very important relationship that we need to be able to know and use and have at our disposal, because when we're talking about salts, this is how we're actually going to get the information for the weak species inside salts. It's how we're going to get the equilibrium constant information. So an incredibly important interaction, an incredibly important equation to know. Okay, so now let's go ahead and let's do some examples, and I'll walk you through the thought process slowly. It's about being able to build the ice tables again, right? The ice tables are going to be fairly simple, nice, easy stoichiometry. Use the 5% rule a lot of the time, but always do your checks to make sure. But again, it's about building up, all right, the understanding of the chemistry to be able to write down the correct reaction. So for example, right, what is the pH of a, let me check, 0.050 molar solution of KF aqueous, right, of KF aqueous. Ka for HF is, let me get it right here. Ka for HF is 7.2 times 10 to the minus 4. Right. So here, we're going to, before we even start writing down the chemistry in the ice table, we're going to break down what we think of this, right? So here are your steps that you're going to follow whenever you're given a salt. Now notice, what we were doing from a recognition standpoint before is we were looking for an H out in front, or a soluble hydroxide, or something that could pick up an H, all right? We see now that we have a metal attached to a non-metal. So just like last semester, just like earlier in the semester, whenever you see that you don't have one of those forms that we were just looking at for acids and bases, and in fact, we have a salt, metal and a non-metal, all right, or something that acts like a metal and a non-metal, then what you're going to do to start the problem is if you see that you have a salt, you do a dissolution, all right? And then what we're going to do after we do the dissolution is we're going to analyze each species. And we're going to decide what we have. Do we have an acid? All right, do we have a base? Or do we have a neutral situation? So whenever you recognize that you have a salt, this is what you do. Do a dissolution, analyze each species, and then you decide, do I have an acid, a base, or is the salt going to be neutral? So these are the questions that we ask ourselves as we do these problems. So here's how it works for this problem. I recognize it's a salt. I'm going to take KF, and I'm going to do a dissolution. Just like we were doing earlier in the semester, we know that KF, when it's aqueous, it breaks down into K plus and F minus. Then what you do is you look at each species and you try to think about, right, where they come from in terms of acid and base behavior. So K plus, for instance, you know that you've seen this from the reaction KOH breaks down into K plus plus OH minus. That's where you recognize that metal with a positive charge from in terms of acid-base chemistry. That's where you've seen it before. You've seen K plus in a strong reaction. It's the conjugate or it's the product of a strong reaction, right? You saw it with reference to KOH. So K plus, if you look at this in terms of its acidic and basic behavior, all right? Can K plus act like an acid or base at all? No. It's a product in this single arrow experiment. It's a product in the single arrow reaction. K plus then is definitely neutral. It's not going to have any effect on our acid or base behavior at all. That's where you've seen it for, then you analyze, or that's where you've seen it from, and then you analyze it in that context. Does it have any acidic base behavior? Nope, just get rid of it. Conjugates of strong species. The results of strong reactions, right, are not acids or bases. And you literally just put an X to them. You remind yourself, hey, listen, it's not going to have any effect on the pH. What about F minus? And there's a big clue in the problem, right? You're given that HF is a weak acid. You're given it's a weak acid because you see that you're given a Ka for it. So F minus, right? This is the conjugate of weak HF. That's where you saw it before. If I do the reaction for HF real quick, just to remind you, right? Try to clean this up a little bit. This is where you saw F minus show up. Does F minus act like a base in this reaction? Sure it does. It's the conjugate base of HF, and it's involved in this double arrow, so it can work things back this way, right? So if it's a conjugate of weak HF, right, HF is an acid, so that means that F minus is a weak base. So we use all those logic structures we developed so far in this discussion, and we say, okay, it's a conjugate of a weak species, so it itself is a weak species. Okay. Well, then if it's a weak species, it must have a KB. So once you identify that, yep, this species right here is going to influence the pH, it's a base, kind of write that down. Your next question is, what's KB? Well, remember, we have a pathway to get KB. If this is a weak base, let me emphasize that one more time, in case it's not obvious. If this is a weak base, because of our analysis of our HF reaction, what's KB? Well, we know KW equals Ka times KB. What are you given in the problem? Ka for HF. So you're given everything that you need. You've memorized KW. You know Ka from the information above. You can solve for KB. Okay? So it's a lot of work up front, and that's what you got to get comfortable with to decide what the correct chemistry is, right? And how to get the correct K. Now we're going to finish this example together, but again, make sure you re-watch this, make sure you kind of understand where all this is coming from, because it's one of those situations, again, if you can't write down the correct chemistry, if you can't look at this and know it's a base and a basic solution, you're going to get the wrong pH. Okay, so with this established, all right, KF really has F minus inside it, and F minus is definitely a base. With all that established, let's write down the reaction, all right? Let's do an ice table. Let's finish this example. KF produces F minus in solution. It's still an aqueous solution. So what does that F minus do? It reacts with water. We decided that F minus was a base. So we know that when it reacts with water, it produces OH minus and the conjugate acid. We know that for sure, right? So we go I, C, E, and we start to fill in this ice table now with the chemistry established like we would last chapter. You're not given any initial information about this. The initial information that you're given is you have 0.050 molar KF. Well, remember what we wrote down before. KF dissociates completely into a K plus and an F minus, and we started our analysis there. So wait a second, from like last semester or even earlier this semester, if I started with 0.050 molar KF, what's my concentration of F minus? Well, all these relationships are 1 to 1. So if I have 0.050 molar KF, then I know my F minus concentration, because one of these breaks into one of these. My initial F minus concentration is 0.050 as well. Okay? So from this, we now have an ice table. We do a Q versus K. We see that Q equals 0. Q is less than K. And where are we moving? Towards the product side. Again, this is the part where the ice tables are actually easy, but it's about getting this correct setup. Okay, so I have this set up now, and all I need is a KB to do this problem. KB is going to be equal to KW divided by KA. KW we've memorized as 1.0 times 10 to the minus 14. Ka we've been given is 7.2 times 10 to the minus 4. If I plug these into my calculator, the number I get is 1.388 times 10 to the minus 11 with two significant figures. Okay. This is Kb for F minus acting like a base and generating OH minus. This is the Kb associated with this ice table. Okay. So we use this relationship to now get a Kb. Why do I need a Kb? I have a weak reaction generating OH minus. This Kb now is a number. And what's it equal to? It's equal to products, right, over reactants. Everything raised to their stoichiometric coefficient. The products are multiplying each other, okay? That's your mathematical setup. It's a good opportunity to use the 5% rule, and I'll just kind of give you the answers, and I want you to fill in the math as we go. If you use the 5% rule, it ends up working. And what you get after the 5% rule, or what I get, is that my x is equal to 8.3333 times 10 to the minus 7th with 2 significant figures. That's what I get for my x. If I take the negative log of that x, that's equal to the POH. If you look at the ICE table, we're generating OH minus. If I take the negative log of that x, I get the POH, all right? And what I get for the POH is I get 6.07918, all right, as my POH. If I then subtract 14.00 minus my POH, what I get is my final answer for this. I get 7.92 as my final answer for this basic solution. Is my final pH, right? A basic pH, always ask yourself that at the end, and the answer is yes. And if it's a basic pH, then it gives you credence that what you did from a chemistry standpoint was appropriate and that your math worked out well, all right? So that's it. So that's how you approach these problems. There's extra steps at the front. I want to do one more setup together and give you one more bit of practice to do, just to kind of see what happens. And then we'll talk about simple scenarios that you'll also see. So let's do one more setup here. So another example. What is the pH of a 3.00 molar NH4Cl solution? Okay, what's that pH? Kb for NH3 is equal to, all right, 1.85 times 10 to the minus 5. Okay, so here's our thought process. Let's identify what's in solution. So I look here. Is it an acid, a base, or a salt? So you ask yourself, is it an acid, a base, or a salt? Well, I see NH4 plus. That's something I've memorized from last semester as something that acts like a metal because it's involved in ionic compounds and it has a positive charge. Oh, wait a second then. If it's involved in, oh, this is an ionic compound, this is definitely a salt. For sure. So what do you do with salts? You go NH4Cl. You know that it breaks down in water. You do a dissolution. It breaks into NH4 plus and Cl minus. And then you ask yourself, in terms of acids and bases, where have I seen these species before? NH4, that looks like the conjugate, NH4 plus, it looks like the conjugate acid of NH3. It looks like, right, NH3 with an extra H plus. So NH4 plus for sure. This guy right here, NH4 plus, is a weak acid. It's a weak acid because it's a conjugate of a weak species. So we must be able to find a Ka for it. All right. Cl minus, where have I seen this before in terms of acids and bases? Oh yeah, when I had HCl, it breaks into H plus and Cl minus. Oh, it's the conjugate of a strong species. And what do we know about conjugates of strong species? They don't influence our chemistry. or acid-base chemistry. Conjugates of strong species get an X to them because in the context of acid-base chemistry, they can be completely ignored. They are neutral, right? So I have a weak acid here. I'm given a KB. It's the same thought process now. Let's write the chemistry, right? For NH4 plus, we've identified it as an acid. Let's write the chemistry for NH4 plus, acting like an acid. Acids react with water to make H3O plus and the conjugate base. All right. So this is the acid behavior. I can build an ice table from there, right? Ka I can get as Ka times Kb is Kw, so Ka is Kw divided by Kb. So it's 1.0, sorry, times 10 to the minus 14 divided by 1.85 times 10 to the minus 5, right? And so what we get out here is 5.4054 times 10 to the minus 10. This is Ka for NH4 plus. All right. Keep track of significant figures. There would be 2 significant figures there. Right, 2 significant figures there. So when I do this problem then, and I want you to do it yourself, right? And check my math and make sure you contact me if there's an issue. But what I get for the pH of this solution is I get the pH is 4.4. Okay. I can build an ice table with this reaction. I know the Ka to use now. I calculated the Ka for the conjugate. My X is going to be H3O plus. All right. Hopefully you can kind of see where things are going. Ooh, wait, significant figure wise, sorry. This is going to be 4.40 at the end in terms of significant figures being correct. All right, try this problem. All right. One last example is an easy example. But it's only easy because you do the appropriate recognition at the top. What is the pH of a 10.00 molar solution of NaClO4? Okay. Thought process again. What's in solution? Is it an acid, a base, or a salt? And so hopefully everybody can recognize that as sodium perchlorate from last semester, from this semester. It's definitely a salt. What do I do with salts? I break them down into, right, their appropriate ions. I break them down completely. I do a dissolution, because remember these solutions are always aqueous for us. I get Na plus and ClO4 minus. I now analyze each one of these and I ask myself, where have I seen these in the context of acid-base chemistry? Well, I know that NaOH is a strong base. So what does that make Na plus? Na plus comes from a strong reaction. It's on the product side of a strong reaction. It's a conjugate of a strong reaction. So if it comes from a strong species, it doesn't affect the acid-base behavior. It's neutral. What about ClO4 minus? Well, this comes from HClO4. That's where you've seen that before. Well, hold on a second. HClO4 is a strong acid. It's one of those on our list that we have memorized. So this is a conjugate of a strong species. And what do we know about conjugates of strong species? Conjugates of strong species do not have any acidic or basic behavior at all. So now, what's in solution that affects the pH, right? And the answer is nothing. We remind ourselves that it's aqueous, right? So then what's the answer? Well, there's no acid, there's no base, there's nothing influencing the pH except for water. So with all my recognition steps, all right, I now avoid a ton of work. And what I say, hold on a second, both these species Na plus, and ClO4 that come from strong species, so they have no acidic or basic behavior. So my solution is completely neutral. And so without any more work, I get to say that the pH is 7.00. Because water is the only thing in there that's going to be affected by, that's going to be affecting the pH. So a lot of very important ideas as always, all right? But there's a bit to do here in terms of wrapping your head around writing the correct chemistry and getting the correct Ks, okay? So it's a step further than what we've been doing before. As always, you're going to practice. You're going to let me know what you need in terms of support.